section, and we'll try to make sure that we cover all those questions, right? All right, so payload, right? So when we talk about payload, really what we're talking about is on the network, how do we make sure that signals interoperate with each other from a like core signal aspect, right? If I have one device on one side of my system and another device on the other side of my system, I need to send audio between those two things. What payload do we use in order to make sure that those two devices are interoperable, right? So standards, right? Standards for interoperability and protocols for audio over IP, right? So first off, right, one of the very common words, terminologies that we hear a lot is AS67. Of course, this is a very common protocol and standard for audio over IP networks, right? Not particularly a standard, but a protocol that's used very, very often, right? Whether it's broadcast or broadcast or live events or AV, it's used very commonly as Dante, right? And then, of course, as a subset of AS67, we also have SMPTE 2110-30, right? So we have these three main subsections of audio over IP that we use kind of on a daily basis. And these are very common to need to be interoperable between the three of them, right? And into an intercom system. When you're dealing with intercom, a lot of times you do have systems that require using all three of these. So let's compare SMPTE 2110-30 to AS67, right? So I already said that 2110-30 is a subset of AS67. So let's look into that, right? So in terms of AS67 versus 2110-30, there's a couple commonalities and some things that aren't as common, right? So in terms of media payload, right? That's the real like uncompressed audio that we're passing over the network. The good news here is that AS67 and SMPTE 2110-30 utilize the same media payload, right? It's PCM uncompressed audio. So it's this uncompressed audio that's traversing over the internet that is a common and is a standard that's existing. And that's what's being utilized for AS67 and 2110-30. The PTP version is the same, right? It's PTP version 2. That's our timing mechanism that we're going to dive much deeper into, in a couple minutes later on in the presentation. The PTP profile is a little bit different. That has to do with how messages are traversing over the network, and so that can cause issues with interoperability, not necessarily. And then some other things to keep in mind with PTP is that AS67 specifically identifies PTP and timing information so that any device on the network could be a leader device, right? When we talk about leader-follower relationship using the best master clock algorithm, any of the devices that participates in AS67 can be a leader or a follower. Versus within the SMPTE standard, it actually calls for every device to have something called follower-only mode, which basically allows us to set any device that's sending and receiving audio to only be able to follow the leader, the master clock, right? So that's just something that is a little bit different between these two devices, right? Connection management, there is a connection management built into AS67. It's typically SIP or unicast. That's what Ravenna uses. They use SIP to establish connections. But in 2110-30, the connection mechanism specifically is to utilize SDP information. And we'll cover SDP a little bit more as we get into the control section of interoperability later on in the presentation. However, there's some additional things that can make 2110-30 even more interoperable, which is NMOS, right? And we're going to talk even more about that later on in the presentation, but ISO 4, ISO 5, those are things that to keep in mind as we kind of walk through this, right? Transport mechanism is going to be unicast or multicast. It just has to do with how it traverses the network. And then 2110 is only multicast. So this, can cause issues, but most of the time we like multicast because it allows us to facilitate better and bigger implementations on our broadcast networks. In terms of payload and packet time, right? With AS67, they basically said, hey, everyone needs to be able to do 1 to 8 channels in a single stream at 1 millisecond packet time on the network. and at 48 kilohertz, right? So that's the mandatory thing. And then whatever you want to do past that, you can do it. You have to be able to do 1 to 8 channels with 1 millisecond packet time at 48 kilohertz. With SMPTE 2110-30, there was a little bit more specification written for that. We have what we call level A, B, and C, right? So level A is the same thing you'll notice as AS67. But they added some additional standards to level B and level C, where level B is 1 to 8 channels with 0.125 millisecond packet time, which is a little bit, it's designed for a little bit more of a stringent network, so like a closed broadcast style network. And then level C, which expands the amount of channels that you can have in a level B type flow that you're passing through the network, right? So what they've done with 2110-30 is they've actually expanded upon a lot of the things that were in AS67 in order to make it a little bit more interoperable between 2110-30 devices, right? Because what we've seen in the past is there's a lot of devices that'll say AS67, but they're hard to interop because of the connection management system and sometimes because of the payload, right? All right, so that's 2110-30 versus AS67. What about Dante, right? So let's look at the difference between 2110-30 and Dante in terms of interoperability, right? Well, the good news about Dante's interoperability is it has increased dramatically over the past couple of years because in 2019, they released a firmware for a lot of Dante devices that allows you to utilize more 2110-centric flows on your network, right? So this is going to allow for a lot more interoperability with Dante devices in a 2110-30 environment, right? So some of these things we already know about 2110-30 that we covered on the previous slide. We've got PCM uncompressed audio, great, right? Very interoperable. PTP version 2. In terms of multicast IP addressing, right? I bring this up because there is a stringency within the AS67 format of Dante, right? You can use any address in what is considered the administratively assigned multicast group, right? So that's 239.0.0.0 all the way up to 239.255.255.255. If you've taken a basic networking class, that's 239.0.0.0/8, right? PTP leader or follower mode, same thing as before. It must be configured. It must be able to be configured as follower only. Connection mechanism is the same as we know before. So then we get into Dante and AS67 mode, right? In AS67 mode, Dante utilizes 2 different versions of PTP, right? Because natively, Dante will only use PTP v1, which is not inherently interoperable with PTP v2. It can coexist, but it's not inherently interoperable, right? And so that's something to keep in mind. And it uses the AS67 media profile, same as AS67 did in the previous slide. In terms of multicast IP addressing, you can only use specific addresses in a specific scope. I think it's 239.69.x.x. So anything 239.69.0.0 to 239.69.255.255, you can implement in that way. But it does constrain what you're allowed to do right on the network. PTP leader and follower, it's selected by best master clock, and it is not configurable for follower only mode in this AS67 mode. In terms of connection mechanism, they use something called SAP, and that's what, if you guys have ever used Dante controller before, in Dante controller, what it's using to actively find all of the devices on the network and make connections is it's using a protocol called SAP. It's a protocol that's it's already been defined and used in other parts of the network industry, right? Similar constraints to typical AS67, right? We've got 1 to 8 channels in a single flow with 1 millisecond packet time at 48 kilohertz only, right? So that constrains us a little bit. However, when they added the 2110 implementation of Dante, a lot of things changed, right? So they changed the profile that they were allowed to use within PTP v2. So now it can use the 2059-2 profile, which is the PTP v2 profile that was defined by SMPTE in the 2110 specification. And it can also use the AS67 profile. So that makes it significantly more interoperable, right, as we move forward. It also uses PTPv1, but as per Dante's 2110 white paper, it will actually default to PTPv2. You can now use any IP address within the 239 range. In terms of leader and follower, it's going to be the same as Dante AS67 as far as we currently know. And it still uses SAP Discovery, right? So but manual subscription is possible, right? So we can actually put all the information in for a stream and subscribe to it. Whereas before with AS67 mode, it would have to, in order to have a Dante device subscribe to an AS67 device or a 2110 device, there was some workarounds that you had to facilitate. Sometimes using Dante Domain Manager, or sometimes using, there's a free tool by Ravenna that's a Ravenna SIP to SAP converter that allows you to basically advertise AS67 devices into a Dante environment. Right? And then in terms of payload time, they've drastically increased their ability to facilitate payload and packet times in terms of interoperability with 2110. Right. So you can see that we're getting to a spot where Dante is becoming increasingly interoperable with 2110-30, which means that, which leads me into my next point, which is islanding, system islanding, right? So what we saw propensity to do with all these different payloads, right, with AS67 and with Dante and with 2110-30, is that people had a propensity to island off a lot of their devices, right? So we have a lot of we have a lot of devices, right? So we've got 4-wire devices in our broadcast system. We've got system boards and matrices in our system. We've got intercom in our system. We've got telephony. We have cameras and we have monitors, and we have, and that exists within the video realm and the audio realm, right? So as I'm building up a facility, right, the idea in terms of connecting an intercom system to all these devices is to island off each of these specific parts into their own network, right? So I have a bunch of Dante stuff. I want to use Dante for my for all of my audio network. So I'm going to do that. I'm going to create a Dante network that's going to connect to my intercom through a specific port on the intercom, right? Okay, well, now I need intercom, right? So when I add in intercom, I'm going to create an intercom network, and that intercom network is going to exist of telephony and panels and wireless belt packs and stuff like that, right? Well, and then now I want to add video, and I want to integrate some of my video, the audio that's going to all of my monitoring and the audio that's coming from my cameras. I want to have that exist within my matrix. So I'm going to create another network that's going to be the video network, and I'm going to add all of those things into there, right? And if you look at, like, from a flow perspective, what this ends up looking like, I've got my audio flows. My audio flows are going back and forth between my 4-wire devices and my mixers. And then from the mixer, it's going into the intercom, right? And then I want to add audio from the video side of things and audio from the intercom network into my matrix as well. So I do that. And then when I want, and then obviously the video is going to exist only in the video network, right? But what ends up happening here is that we've created this world in where we have separated networks with pieces of equipment that are bridging the gaps between those networks in specific ways in between those, right? So to get audio from the Dante network all the way over to the video network, I have to find a device that's going to convert it into something that I can send over to the video network. So I have a ton of piecemeal devices that are in between all my network islands that are causing issues with either latency, or they become points of where you can get into trouble with like pieces going down. So redundancy is a factor, right? And then of course, then we add telephony into that, and stereotypically telephony is VoIP, so that's going to have to be a little bit separate. So we have a different kind of flow going down into VoIP, right? So what we've effectively done is we've created islands, right? We have an audio island, an intercom island, and a video island. And to get there, we have to use the ferry that goes in between them, as opposed to having one big island, right? Where everything coexists and everything sends its signals into, right? So I've got all these devices sending their signals into the network. And then when I want something out of the network, I pull it out, right? So I've got all my monitoring systems that gets video and audio flows that come from the intercom system. But if I need those specific audio flows to come into my intercom system, they come in and I can subscribe to them and it's the same exact flow, right? So I can create a system where instead of islanding everything off, I have a system at the very center that everything comes to. It's easier to troubleshoot. It's easier to manage from a centralized standpoint. And also something that we'll talk a little bit about later is much easier to secure a single network and monitor a single network than it is to worry about 3 separate networks, monitoring 3 separate networks, and securing 3 separate networks, right? Any questions on payload interoperability before we move on to timing interoperability? I don't see anything, but I'm going to take a quick drink of water and then we'll move on.
And just remember, folks, if you do have any questions, just drop them into either the Q&A or chat windows and we will try to get to them.
All righty. We will go ahead and move on. If I see any questions, we can always circle back to stuff from previously in the presentation. So not too worried about it. All right, so interoperability in terms of timing, right? Well, in a network, the main form of timing is going to be PTP, right? And so that's something that a lot of us have dealt with. Sometimes hard to get your hands around a little bit because it's very different from kind of what we're used to. But PTP in general, let's just cover a little bit of the history of some of this PTP stuff, right? So the idea of PTP, which was is an IEEE specific standardization called 1588. The idea of it was it's supposed to replace the SPG, right? So instead of generating analog video signals for blackburst and for tri-level, we're going to utilize packets to time things down to the nanosecond, right, between all of these devices. So this was started by the IEEE in 2002. That's why the PTP v1 specification is called 1588-2002, right? And it was really created to synchronize like financial transactions on Wall Street. And if there's anything we know about financial transactions on Wall Street is they have to be perfectly in time. And so that is why PTP v1 was kind of introduced at the beginning, right? Ultimately, it ended up being adopted by a lot of different industries, mainly anything that needs precise timing but doesn't necessarily have access to like satellite navigation signals, right? So mobile phone tower transmissions when we're going through the desert and passing between, cell phones, cell phone repeater to cell phone repeater to cell phone repeater, all that needs to be timed enough to allow you to pass between one antenna and the other antenna and not lose or drop your call, right? So that's kind of PTP v1. In 2008, they started a new specification for 1588-2008, and what that does is it improves the accuracy and the precision and the robustness of PTP in general, right? The idea was that PTP was very good, but PTP v1 wasn't the most scalable thing ever. And so the idea behind PTP v2 is to create a system that was more scalable and more robust. But the only problem is that natively it was not backwards compatible with PTP v1. And again, I do want to clarify, it's not that they can't coexist together. It's that a PTP v1 device can't subscribe to PTP v2 and use all of that data for timing information, right? It's just something that they can't necessarily do. However, PTP v1 and PTP v2 can coexist in the same network. In fact, that's gotten a lot easier as we've kind of moved along. So PTP in general, I won't spend too much time on this, but I do just want to cover it. It's the specific multicast group. It exists with a number of different messages that we'll cover in just a second. It's the sync message, the follow-up message, the announce message, the management message, delay request, and delay response, right? And all of these are pretty important. Management, less so important, but most of these are incredibly important towards how PTP works and the communications back between those things, right? And then in terms of PTP, they created this thing called hybrid mode, which further makes PTP v2 a little bit even more robust, right, than PTP v1, where a lot of times with PTP v1 devices, they found that they would overload their PTP engine because they were getting too many multicast messages. So what they did was they took what was the bulk of those multicast messages, the delay request and the delay response, things that didn't necessarily need to be multicast, and they allowed you a mode to make them unicast, right? So an environment where you're struggling with how many multicast messages are being created by PTP, you can mitigate that a little bit. So let's talk just briefly about how PTP works, right? So I've got a leader and a follower, right? They're moving down the list at different times, right? And the leader identifies this. We've got the leader running at 12:00:01, the follower running at 11:59:41. How do these guys sync up, right? Well, first we have the leader send out a sync message, and at the same time it sends out a sync message, it also, let me get my laser pointer. It also takes a timestamp. It doesn't send the timestamp yet, but it takes the timestamp and sends the sync message out. The follower receives the sync message. It takes its own timestamp. So it's got 11:59:43, right? And then the leader then says, hey, by the way, this was here's my follow-up message to my sync message. This is when I sent the sync message. Now, the reason that it doesn't send it with the sync message is to accommodate the idea of it being as close to the accurate time as possible when the sync message left the interface, right? So that's the concern there, is that if the sync message left with that timestamp on it, the timestamp would be a little bit off in some way, right? So we receive, as the follower, we receive that timestamp. We do a simple calculation, it's just a delta calculation, right? And we find out that we're 18 seconds off, right? So we add those 18 seconds onto our current time, and we realize that we need to be at 12:00:03. Great, we should be in time, right? Well, unfortunately, there is a problem, right? There was a bit of network delay, right? From the time that the sync packet was sent to the time that it was received, there was a little bit of time. It's not typically 2 seconds, but in this example, we'll just say that it took 2 seconds for it to get to the follower device. So what happens is the follower is going to take a timestamp, and it's going to send what it calls a delay response. The leader is going to say, hey, I'm going to take a timestamp when I get that delay request. Sorry, it's going to send a delay request. And when that delay request arrives at the leader device, it's going to take that timestamp and it's going to send that timestamp back to the follower with the delay response, right? And then we're going to do a simple calculation again. We're going to divide it by 2 because that's both sides of the network delay. And we're going to realize that we are 2 seconds off, right? So when we're 2 seconds off, we're going to add that to what our time would have been, which was 12:00:11, and actually we're 12:00:13, right? We're adding it to that 12, what we would have been 12:00:11. So in very short words, this is kind of how PTP works, and this is why it's so important. We're keeping all these devices synchronized down to the nanosecond, right? All right, so that's how that works. If you remember in the payload section of the presentation, I was talking about BMCA, right? And how some devices use BMCA, and SMPTE 2110 devices have to have an option to turn BMCA off and be follower only, right? So BMCA is a protocol, it's an algorithm that was baked into PTP that allows for any device on the network to elect to be the leader device, or the GM, the grandmaster, right? So that is a list of these devices, right? Or a list of these things right here. It goes down this list. So this is from most important to least important, right? So first it looks at a firmware programmed in, baked in piece called priority 1. And then it looks at firmware programmed in clock class, clock accuracy, variance. And these are usually defined by the manufacturer and firmware and baked into the firmware, right? It's not something that we can change as users typically. And priority 2 is the one thing that we can change, right? So this allows manufacturers to say, hey, even if you are participating in BMCA, we want you to be a follower device no matter what. So they make their priority 1 a super high number or a super low priority, right? And then they know that it'll never take over as the GM, right? So this is important to know, right? As we interop a lot of 2110 devices with AS67 devices, it's important to know what devices participate in BMCA and what devices don't, and maybe what the priority one is, so that we can make sure and not have a situation where we put everything onto the same network and we have a bunch of different devices trying to fight over who's going to be the GM today, right? So let's talk about a couple of things. So I want to talk about switch infrastructure, right? Because PTP is very important, and switch infrastructure is very important to PTP infrastructure, right? So there's two main types of switches that we want to see in a PTP environment, in a 2110 environment, right? We have a boundary clock, which we're going to talk about right now, and then later we'll talk about a transparent clock. So in a boundary clock, it's what is going on is inside of a switch, there's some mechanism to synchronize our leader to our follower device and to cascade that down among a bunch of different switches. And this is the way that it works, right? If I'm a GM or a leader device and I know that I'm running at 12.0.0.0.4, what I'm going to do is I'm going to send that information using PTP to the switch. The switch is going to actively make the port that I'm connected to them on a follower port. And that terminates the PTP relationship between the leader and the switch, right? Right there, no packets pass after that. It gets to the follower port, it's going to synchronize the switch, and then instead of forwarding the packets through to the follower device, it's going to start a new PTP relationship with the follower device by making its port a leader port. And the follower is going to subscribe to that leader port and synchronize to that leader port. And what this does is it creates a lot of devices on the network that are all synchronizing to the leader device and cascading their clocks down, as opposed to creating network delay of the PTP packets that are being forwarded through, right? So in this instance, we have a leader and a follower device that are both in sync using a boundary clock, right? So boundary clocks, just to recap, a boundary clock switch terminates the PTP connection from the leader and creates a new PTP connection on the other side of the switch, on the downstream of the PTP, right? And it does that in order to remove what is called PDV, or packet delay variations, between itself and the next upstream clock. So between itself and the leader device, or maybe itself and another switch that's connected to the leader device, it's going to remove whatever packet delay variation there might be between it and whatever it's connected to that is its leader, right? So the good news is about boundary clocks is that every device on your network can be a boundary clock. Not necessarily, there may be hard limitations to that, but the idea is that everything participates within PTP in order to keep as tightly a synced system as possible, right? And so what this does is it allows for slightly larger networks, or significantly larger networks, because you're not having to worry about how is this PTP flowing from the leader device through X, Y, and Z switch down to the follower device, right? Instead, you're just worrying about, is this switch synced to the upstream switch? Is that switch synced to the leader device? And typically, all of these things are going to kind of, once all of the configuration is done, these things are going to fail over in a very transparent way, right? So the difference between a boundary clock and a transparent clock switch is that the transparent clock switch doesn't take quite as active of a role, right? It still forwards that information through the switch, but it has a nice little trick that it does in order to facilitate active clocking for the leader and the follower device, right? So I've got my leader device, I'm connected to the switch, my time is 12.0.0.0.4, right? I'm going to send that information using PTP into the switch. And what's going to happen is the switch is going to take a nice little timestamp. And with that timestamp, it's going to save it, and it's going to push the packet through the switch, and it's going to take a timestamp as it hits the other interface, right? And it's going to make a quick calculation of how long it took to process that packet through the switch. In this case, between 12.0.0.4 and 12.0.0.6. And so it's going to say, okay, well, it took us 2 seconds to process it. So what's going to happen is it's going to apply that actively to the PTP message, right? So now instead of sending just a PTP message, we're sending the PTP message plus the processing time that it took for that PTP message to traverse the switch, right? And so once that gets to the follower device, well, it's a simple calculation by the follower. We take the time that we got it, we take the processing time, we do that calculation, and now we're in sync, right? So you can see where this is very effective, but it also, from a scaling standpoint, can be a little bit cumbersome, right? Because we still have a little bit of that, all of the onus of clocking everything is on the leader device, or the GM, as opposed to in a boundary clock system where all the onus is on everything, as opposed to specifically the leader or the GM device, right? So this can be a little bit more scalable in a lot of situations. The boundary clock can. So PTP aware transparent clock switch, right? So it takes into consideration processing time incurred within the switch. It modifies that packet as it flows through the switch, and note that it only modifies its packets that flow through it specifically, and it adds only its own processing time. It's not like it's adding its processing time plus a couple upstream switches and modifying theirs. It's just doing its own packet modification, right? And it doesn't terminate that PTP connection, right? So boundary clock terminates it and reestablishes it. Transparent clock does not do that. It just forwards the packet and adds that nice little timestamp to it. So this is not as scalable, right? And it's not as scalable because we still run into that same issue that we talked about before, where packets can be, like, you can be overrun by the amount of multicast, and all the onus is on the GM, so that can get cumbersome for the GM, and sometimes the GM can't go up to a certain amount of follower devices, right? So this would be good for small to medium-sized networks. Or what we see a lot of people do is we see a lot of people implement transparent clocks at their center, right? And then as you branch out from the center, you have boundary clocks that integrate into your transparent clock. So you have your GM syncing all of your boundary clocks hanging off of your transparent clock, but not necessarily clocking every single follower device, right? And in reality, that network is going to look a little bit more like this, right? So what we see a lot of times is that the whole network is boundary clock. Maybe sometimes these are transparent clocks. It really depends. And then we have some aggregates that are boundary clocked off of these core switches, these spine switches. And then we have our nice little access level switches for our IP audio, right? Our intercom connected to both of the AGs redundant from a redundant standpoint. And at the top, we have the PTP GM connected directly to our cores, connected to GPS, right? So this gives us a lot of ability to make some really nice timing systems between all of our gear, right? And it's really important that all of this gear on our network interops with our PTP, right? And uses the same PTP, and we know this so that we can get all of those devices on the same page, right? So questions. So I see a couple quick questions. 2110-31, anything we need to take into consideration as opposed to 2110-30? Sure, yes. 2110-31 is specifically an AES-3 payload going over, encapsulated into an IP packet and traversing the network. Generally, things that say 2110-31 are interoperable. It's a little bit easier to manage with that because it is specifically just the AES-3 payload encapsulated, right? And there's not, there aren't, we don't see 2110-31 adopted nearly as much as 2110-30. There are some manufacturers that definitely have adopted it, though, are Dolby. They were in charge of getting it in there, right? And they use it significantly as a way to aggregate their Madi and their user bits alongside of the media payload, right? We use it for some of our panels. It's used a little bit here and there, but a lot of the times it's natively interoperable. I haven't dealt with a situation where 2110-30 was really weird. Similar things to keep note of, though. Timing is a really big thing there, so PTP needs to be kept up with and stuff like that. Another question is, can you go over the difference between one-step and two-step? Yes, absolutely. So two-step, what I was explaining, PTP one-step versus PTP two-step, what I was explaining was actually two-step PTP. Right. This is when a sync message is sent without the timestamp on it, and then a follow-up message is sent after that with the timestamp on it, and then we have delay requests and delay responses going back. Right. One step which is a little bit less common, is when the sync message actually does have that timestamp in it. So it takes that timestamp and it sends it out, and then it arrives at the interface all at the same time, right? So it's I explained two-step specifically because it's a little bit more common, and it's common in some of the a lot of the implementations that I've been a part of. Any more questions before we move on? What alternate real-world master timing signals can these systems use if bad actors interrupt GPS service? Right. That's a really good question. So couple things to note there. And I'll just go to this slide so that we see something interesting while we're talking about this. A couple things to note there. There are services that actually provide PTP to locations in order to provide them with time of day, right? And so those would be good for that. A lot of those are GPS based at some level, but typically they're GPS based off of a number of different locations and different technologies in different places in the world. And what they do is they will get you PTP in order to get an accurate time down to they're probably more microsecond based than they are nanosecond based. However, something to keep in mind is a lot of it depends on the gear. A lot of audio gear doesn't care about time of day. A lot of the AS67 and 2110-30 devices don't care about time of day as much. And while GPS is very important for a lot of devices to keep in sync between maybe facility to facility, PTP doesn't natively need GPS in order to run. Now, in order to have accurate time of day measurements, it would be highly recommended to use GPS and then maybe one of these PTP services that provides you with PTP as a backup to that. And a lot of those services are sold specifically as either backups to GPS, or if you're in a location where you can't get a GPS signal, right? So we're talking a lot of like military contractors and just different locations in the world where it may be harder to find the amount of GPS antennas that you need for that time of day information. So hopefully that answers your question. Any more before we move on? I'll take a quick sip of water. All right, control. All right, so this is this is where a lot of it gets a lot of this comes together, right? So timing, like most everything utilizes PTV2 now. Control is where we have some of the make or break stuff, and this is where we find it. This is one of the most important pieces of a lot of facilities in terms of intercom and in terms of just the whole facility as a whole, right? So control from a top-down perspective, right? We utilize SDP in 2110 environments, and AS67 utilizes SDP as well, but it's a protocol that it was previously designed well before SMPTE 2110 was being proposed, and it's utilized because it's so proven, especially with VoIP services and all this kind of stuff, to connect multiple different pieces of equipment together, right? So in a traditional approach of connecting pieces of equipment together, right, what we would do is I'd go into my settings menu, I'd put in the IP address, I'd put in the multicast port, I'd put in the bit depth, the packet time, the receive buffer, I put in all these things, and you click OK, and you kind of hold your hands together and pray a little bit, that's the traditional approach, right? The SDP file, what it does is it allows us to see all that information in a condensed text-based way, right? And because this is text-based, it means that we can take it and we can send it via HTTP requests across a network and send it back and forth between devices. So this makes it extremely easy. You'll notice that you see a lot of the same information that we were just talking about here in this SDP file, right? We've got our audio, we've got our port, we've got our payload, we've got our we've got our bit depth, we've got our 48 kilohertz, we've got how many channels are in it, right? So all of that information that we could have put into that settings window, we now use an SDP to transfer between things. So typical 2110, this is actually a -20 flow. And what we see here is that we've got all of that information. All that information kind of facilitated throughout this SDP file. We've got our payload ID, we've got our sample rate, we've got our width and our height, our bit depth, our color telemetry, all that kind of stuff is available there, right? So this is another example. The nice thing about an SDP file, right, is it also allows us to have primary and secondary, right? So what I can actually do, what you'll notice is in this example of an SDP file, well, this is a video SDP file, it identifies that we can have an SDP file that has both a primary flow identified and a secondary flow identified, right? So in a traditional approach, we'd have to identify both of those flows separately. In an SDP information world where we can just take an SDP and load it in, we can actually just put the SDP in and it'll populate both of those fields, the primary and the secondary, right? And you'll notice that all that stuff is the same exact stuff that you can put in here, or we can just click here to import an SDP file, right? That's all fine and good, but monitoring 3,000 SDP files and saving them on some piece of your some hard drive somewhere and then using them to identify a bunch of different hosts, that's not a very scalable solution, right? So that's where we move into NMOS. NMOS is one of the things that really helps us be interoperable with other people just in general. And in and of itself is a very open protocol that allows us to be interoperable even within that, right? So there are a number of NMOS specifications, right? So NMOS has identified a bunch of stuff that's there to help us with interoperability, right? They have what we call interface specifications, right? So they have a bunch of them. There's ISO 4, which is discovery and registration, ISO 5, device connection management, and ISO 6, network control, right? We'll talk at length about these in just a moment. They have ISO 7, which is event and tally, which we'll go over briefly. ISO 8, which is great because it allows us to interoperate audio mapping, right? So if I send a flow into the network that has 4 channels, the first one's program, the second one's an IFB, and the last 2 are microphones, I can have the receiver interpret that. He can take it and interpret it as channel 1 is a microphone, channel 2 is a microphone, channel 3 is program, and channel 4 is an IFB, right? So that allows us to dynamically map a lot of that stuff when we're having issues with specific devices needing specific things at specific times, right? So that's ISO 8. ISO 9 is also really exciting because it allows us to change settings on external devices through this API, right? So it allows us to reboot devices from an NMOS controller. It allows us to change IP addresses from an NMOS controller, send configuration changes from an NMOS controller. And I would say arguably one of the most important pieces of NMOS right now, I mean, they're all very important, but something that I'm quite passionate about is ISO 10 or IS10, which is authorization, right? Authorization is incredibly important, especially in the day and age that we live in. Security is becoming a much larger piece of a lot of these broadcast infrastructures that we're working with, right? And then IS11, which is a work in progress still, but it's sync metadata processing. So it's basically just a protocol for how to pass metadata between multiple devices, right? All right, cool. So NMOS in general, what is NMOS? What's the idea behind it? So ISO 4, 5, and 6 are kind of designed to be 2110's search engine, right? So there's 3 components to ISO 4, 5, and 6. That would be ISO 4, 5, and 6. We have our discovery registration, we have our connection management, and we have our network control. Now, I like to think of this, and a lot of my colleagues like to think of this kind of in terms of the analogy of DoorDash, right? So the DoorDash app, how does a pizza restaurant go from getting their menu onto DoorDash all the way to it arriving at a consumer's door, right? So first, ISO 4, right? The pizza menu has to be published onto DoorDash. So I'm going to I as a device, as a business owner, I'm going to contact DoorDash and say, hey, here's my pizza menu. Please put this pizza menu on your app, right? DoorDash says, great, sounds awesome. And then DoorDash presents to a consumer the menu, right? They present the menu to them, and then that consumer can say, I want this pizza to arrive at my door, you know, in X amount of time. And so they do that. They order a pepperoni pizza, right? And then ISO 6 comes along and says, hey, DoorDash driver, I'm going to have you as the DoorDash driver pick up this pizza and arrive at that address. And by the way, you're going to take this route to get to that address, right? They're going to give them Google Maps, and Google Maps, as part of the DoorDash API, is going to tell them how to get there, right? So this is kind of a decent-ish analogy of like a little bit about how all these things work, right? And okay, so ISO 4, a little bit deeper look into ISO 4, right? ISO 4, basically just imagine it as a server connected to a network, and that server is advertising itself over a couple different ways. And one of those ways, so of those three ways, you can either manually advertise, where every device you type in an IP address, or you can dynamically advertise through either DNSSD through a DNS, or you can advertise through MDNS. Personally, MDNS is probably the least useful of all of those because it's less scalable and not routable, but that's kind of a conversation for another time. So let's just say we're using MDNS because it's a little bit easier to explain for the moment. And we'll say, hey, all these devices connect to a network. ISO 4 registry says to the network, I'm a registration server. If you have any information that you would like to tell me about, you should tell me. These devices are, this is a monitor right here. This is a video camera sending information into the network. They're going to subscribe to that MDNS and then send all their information into the network using what we call RESTful API, right? RESTful API is a very common API that uses HTTP requests to send and receive information among in many different ways, right? But what's going to happen is these devices are going to say, hey, registration server, here's all my stuff, right? So for example, let's take a look at a very common freeware NMOS commissioning controller from NVIDIA. This is based off of the Sony and the freeware Sony NMOS controller that you can actually download and implement yourself if you are so inclined. You can go to the AMWA website, find a link to it, implement it anywhere you kind of want to. This was designed specifically to run on a Mellanox switch, or NVIDIA switch natively, and so that you could kind of get a head start with commissioning inside of NMOS, you know, on day one, right? So this is our commissioning controller, right? So we have it. I've got my API. I'm going to point all of my devices to nmos.mnip.net, right? So that's just a fictitious host name out there, and this is what this is going. That's what this website is. This is nmos.mnip.net, right? So first of all, I'm going to resolve that. And I know that IP address is like a specific IP address. In fact, it's 10.42.10.20. And I'm going to point all of my devices to that. So I'm going to say, hey, register to this NMOS controller. And I'm going to tell my other device, I'm going to say, hey, by the way, register to this NMOS controller. And guess what? Then I go to my NMOS controller and I can see those devices and I can see everything about them, right? I can see their I can see all of the flows that they have activated. I can see everything that they could in the future have activated, all that kind of stuff, right? So that's ISO 4. That's all it is, just discovering all these things. Then we've got ISO 5. So how does ISO 5 work? All right, well, I've got my three pieces. I've got my camera, I've got my registry, and I've got my monitor, right? But how do I get video from the camera to the monitor? Well, that's where the ISO 5 control system comes in. Now, a lot of these things are all built in together, but a lot of these things are all built in together. But let's just say, for example, these are two different devices. There's one ISO 4 registry server and there's one ISO 5 server, right? So what I'm going to do as a user of the ISO 5 server is I'm going to talk to my device and I'm going to say, hey, I'm going to talk to my camera and I'm going to say, hey, camera, give me your SDP file. And also start sending your video into the network. So the camera's going to say, all right, sounds good. Here's my SDP file. Here's my video into the network. No one's subscribed to it yet, so it's just sitting in the network. And then what I'm going to do is I'm going to go to my monitor and I'm going to say, hey, here's an SDP file. I'm going to post that SDP file to you, and you should subscribe to it. And guess what the receiver does? He sends out an IGMP join. He subscribes to that multicast group, and that multicast group comes from the network and sends right back down into the monitor, right? So an example of this, there's a lot of ISO 5. There's a lot of ISO 5 options out there. Like I said, there's some freeware ones that are downloadable. One of the freeware ones that's most accessible to me is the NMOS Explorer, Riedel's NMOS Explorer. Freeware, not like a sold thing or anything like that. So what I've done is you can see that I'm querying nmos.mnip.net. So that's our API, right? Our ISO 4 API. And I'm going to turn it on right up here. And what I get is I can see those two devices, right? I can see the nodes, I can see the devices, and I can see a nice little list of all their senders and receivers, right? And you can see that it's statically querying that NMOS server that I've set up, right? So it's as simple as that. And now all I have to do to make a sender go to a receiver is drag from the senders to the receivers. And this is pretty common among a lot of these ISO 5 applications, right? So that's all fine and good. ISO 4, ISO 5, real easy, all that kind of stuff. ISO 6. So ISO 6 is a little bit different. ISO 6 is a ratified IS, right? They've NMOS has released their interface specification. It has a lot of good information to it. However, it's not being implemented by a lot of switch manufacturers right now because switch manufacturers have their own systems for identifying and APIing systems to interact with them and dynamically route sources and destinations and stuff like that, right? So Arista has their own product that has handles into the Arista fabric. Cisco Nexus has their own system that has those API handles into the Arista fabric, right? So that's all stuff that would be implemented within ISO 6 that is now realistically being more implemented within a broadcast controller. But the idea of it is, right, is like there's a lot of manual configuration that's going to happen on these control planes on each of these switches, right? And so when I have a device connected right here and I'm subscribing to something and I need to subscribe to something up here, I have to send a join. That join has to go from this switch to this switch, and it has to reach this device, and then it's going to send its data down that way, right? And the idea is instead of allowing the switches to kind of control themselves, we're going to remove that to a redundant but centralized point where the controller machine is telling them kind of what to do. And in this kind of example, what we would do is we'd have a broadcast controller that talks to their API, like an Arista API, a Cisco API, and says, hey, by the way, instead of routing using an IGMP join, I'm going to manually route you from this switch to this switch to this switch. And that way I know a lot of different things, right? I know how much bandwidth is being used on that, by that stream and on those specific links. And so I can mitigate a lot of security issues within that, and I can make sure to manage traffic flow, right? So there's a lot of really good things that we can get from not necessarily ISO 6. It is, ultimately we could get a lot from ISO 6, but we're getting a lot from just the ability to, facilitate a lot of this through static associations, right? So the goal is to have, right, ISO 4, ISO 5, and ISO 6 all working together to make a very cohesive environment, right? Senders, receivers, controllers, and a registry, right? So that's ISO 4, 5, and 6. I just want to briefly talk about ISO 7 because it is a really good way to integrate control in your network, right? So it has to do with tally and events, right? Basically, like, how do we get GPI and tally to traverse an IP network in a standardized way? And that's what ISO 4 has, right? And so one of the ways that people have chose to implement that is through like APIs and stuff like that, right? So in certain hardware, what you can actually do is you can connect it to existing broadcast control technology and identify specific ways to control other things through ISO 7, right? So I could have one device operating as another device and being a control panel while also being an intercom panel, or also being, an audio monitoring panel or something like that, right? And this gives me a lot of control to monitor my system and interop with other devices and get alarms and monitor and have security and stuff like that. So these are the main interoperability considerations, right? Payload, timing, and control. The key to IP intercom interoperability is removing payload limitations, which means like we were talking about, don't island the network, don't create multiple different network islands that you can't move signals between handily. Keep protocols as open as you possibly can. Remove your timing limitations. Make sure all of your things use as similar PTP implementation as possible, and make sure that everything is using its preferred PTP implementation, and which is much more possible in the boundary clock kind of situations. And then remove control limitations, right? So implement open control protocols and open control facilitations. I would always aim for implementing some sort of monitoring system. It's much easier to troubleshoot. And as we move into a much more secure IP world with InfoSec breathing down everybody's backs, which is both a good and a bad thing. It's the CIA, the confidentiality, integrity, and availability. The availability is getting very hard for everybody, but it's getting much more confidential, and the information is always integral, right? So that is IP intercom interoperability today. Is there any questions that you guys have? Let me look through here really quickly. I don't see anything.
I haven't seen any additional questions coming in yet, but certainly if anyone has any, now would be the time to drop them in the chat window.
I didn't know that it's Pi Day today. That's quite exciting.
Well, Steve, that was a wonderful presentation. I think you've given all of us quite a lot to think about and try to figure out, how to move forward when these things come up in the future for the folks who are out there in the field needing to deal with them.
Yeah, thank you very much. I appreciate that.
So any last words from you?
Not necessarily. If you guys have any questions or comments or anything that you guys would like to chat about, feel free to contact me. I am going to pass along this presentation along with some contact information over to you guys, and that way it can be sent out between everybody. So
that's great. And we have also been recording this, so we will have that recording. And for anyone who wasn't able to stay for the entire thing, or who joined late, or if you know of other SMPTE members who may want to listen to it, I will be sending out information on how to access that once I myself figure out how we access those things, because typically Bob would handle that, but I will work with the folks in New York to sort that out.
Sweet. Awesome. Cool. Well, thank you so much. I really appreciate it.
All right. Thank you, everyone. Very much appreciate your attendance today. Take care.
Thanks, everybody.